Yep, so we've got Drew Reiser now. He worked the summer on a project with Wang, Philip Chu, and Ayumi Fujisaki-Manome. And we're excited to hear about your work, Drew.
All right, so I'm Drew Reiser. I'm going to be a senior at the University of Illinois in Urbana-Champaign, and I worked with GLERL scientist Dr. Wang and Philip Chu, as well as CIGLR scientist Dr. Ayumi Fujisaki-Manome, on the development of a multivariable regression model of the Arctic summer sea ice coverage using 6 teleconnection patterns. So the first, I'd like to get some groundwork. Arctic sea ice coverage and thickness is generally controlled by air temperature, which is heavily impacted by external and remote forcings from teleconnection patterns. Our work seeks to create a model that will incorporate relevant teleconnection patterns to improve ice forecasts and ice coverage information in the Arctic region. This will allow us to create a tool in protecting the Arctic region. And as you can see, in 2007, there was a minimum, and then shortly after that, only 5 years later, there was another sea ice minimum, and this just shows the importance of needing to have a tool for forecasting the ice coverage in an ever-changing climate. So our motivation for this was that in past projects, most of the research done has been more of a qualitative aspect of how teleconnections affect ice coverage in the Arctic. And so we want to turn that qualitative aspect into a more quantitative aspect. This will be done by the development of a model that we initially use for hindcasting to see how valid it works, and we will eventually use that to forecast ice coverage. This will provide vital information for activities that take place in the Arctic, such as commercial shipping, recreational ice fishing, and navigation during the winter and summer seasons. It is especially important now because of increased variability of ice coverage in the Arctic region. So the indices the teleconnections that we decided to look at were the Arctic Oscillation, the Dipole Anomaly, the North Atlantic Oscillation, the El Nino Southern Oscillation, and the Pacific Decadal Oscillation, as well as the Atlantic Multi-Decadal Oscillation. And we looked at 6 different areas as well as the whole Arctic. So we looked at the Chukchi and Beaufort Seas, the East Siberian and Laptev Seas, the Central Arctic, the Kara and Barents Seas, the Greenland Sea, the Baffin Bay, as well as the whole Arctic. And we did this over 5 different time periods, which are 1948 to 1978, 1979 to 2017, 1948 to 2017, 1865 to 1978, and 1865 to 2017. We decided to choose these 5 different periods because in 1948, that is when data started to be collected for the Arctic Oscillation and the Dipole Anomaly. And then in 1979 was a nice midway point kind of between the start of that and up until when the data ends for us is 2017, as well as 1979 is when satellite observations started, so the data started to be more accurate. And then 1865 was the last chooser because that is when the other 4 oscillations that we looked at also began. So here are the general areas of the patterns, and so the AO is generally a pattern of pressure anomalies surrounding the North Pole. The DA is characterized by a high pressure system over the Arctic regions of North America and a low pressure system over regions of Arctic Eurasia. The NAO is characterized by fluctuations of difference of sea level pressure between the Azores high and the Icelandic low. ENSO is characterized by changes of winds and sea surface temperatures in the Central Pacific. PDO is sea surface temperature changes in the Northern Pacific. And then AMO is changes of sea surface temperatures in the Northern Atlantic. Second. So first, we plotted out all of the observations, and then we analyzed all of them. So as I mentioned earlier, there is increasing variability, which can be seen very well in the top right graph. As you see, since around the late 90s, it has steadily declined as well as just having very large year-to-year variability. And as I also just mentioned, there is an accelerated trend of decreasing ice coverage in the Arctic. So nailing this tool down will be very useful. The left side graphs are the individual area ice coverages, and from top to bottom, it is the Central Arctic, then the Chukchi and Beaufort Seas, the Siberian Sea, and Laptev Seas. The fourth one would be the Kara and Barents Sea. The next one down, which is kind of hard to tell between the two bottom ones, are the Greenland Sea and Baffin Bay. So first, we needed to figure out which teleconnections impacted which areas the most. So we did this using scatter plots and setting up a linear, a nonlinear, and a quadratic regression patterns for each teleconnection within each area and each time period. In general, for our tool, we decided to use an R value of around 0.1 to be significant enough to include in the model. As well, on the graphs is included a 90% significance value. This was generally used to show like which teleconnections had the strongest impact on the models, so that we would know like definitely to include those ones. Currently, you're looking at the whole Arctic area scatter plots for the 1979 and 2017 period. So once we had all the scatter plots down, it was really just looking at the R values to find out which ones were important. And then we ended up creating an equation based off of those. We created two different models, the first of which is shown here. This uses all 6 teleconnections and then the other model uses the 4 teleconnections of NAO, ENSO, PDO, and AMO. This one, the one that is shown, is the model for the 1979 and 2017 whole Arctic period. And then each equation in the line represents something different. The first line is the interannual variation of the teleconnections. The second line is then the interaction of the interannual variations. The third line is the decadal variations. The fourth line is the interaction of the 2 decadal oscillations. And then the fifth line is the interaction between the interannual and the decadal teleconnection. So then that was the full model, and then this is an example of the 4-index model for the same time period. The lines are all the same, but it only includes NAO, ENSO, PDO, and AMO. So then here we have all 8 possible variations of the models. Generally, the scale of each model doubled that of the highest individual teleconnection, which is really promising considering we don't need to just try to use one teleconnection or like 2 teleconnections to try to predict, but we can use all of them in ensemble to create a very fairly accurate model, considering all of the virtually every model well exceeded the 90 and 95% significance values that we included on all the graphs. So the scale in general, the scale of the full 6-index model was the highest by far. And then the next one down is the 4-index model, which generally had fairly accurate scale. And then the bottom line is the 4-index model, but extended for the entire period of time from 1865 to either 1979 or 2017. And generally, those models were less accurate and on occasion were less accurate than either AO or DA individually, considering they were not included in the graph or in those models. If anyone would like, I also have, at the end of the presentation, I've included all of the 6 area models, as well as the whole Arctic, again, if anybody would like to see at the end of the presentation. So after we had the model set up, we decided to do 2 comparisons. The first comparison of which is shown here. So for the 4-index model, we decided to use the regression-based model versus a blind model. Sorry. The regression-based model is based off of our regressions that we found earlier and is essentially the standard model. The blind model then uses all terms that physically make sense, but just putting them all in blindly rather than using the regression to see if anything was actually important. Thankfully, the skill between the regression-based model and the blind model was negligible, so we decided to just stick with using the regression model rather than using the blind model. The next comparison that we did was comparison between different data sets. So all of the equations are based off of our training data, which is the top model, as you can see right now. We decided to do this test because it would show the validity of the models if we used the same exact equation that we found for the training data and applied it to different reconstructions of the same area. For this, we used data from Walsh et al. In 2017, as well as Brennan et al. In 2020. Both of these, however, only provided reconstructions of the whole Arctic region, but that was fine. In Walsh's data was a reconstruction that was defined as the sum of the grid cells multiplied by the ice concentration and averaged north of 70 degrees of latitude. Brennan et al. Sea ice data was defined as areas of ice concentration of at least 15% and averaged north of 65 degrees north. Almost all of the new data, or the Walsh et al. Data and the Brennan et al. Data, actually surpassed the significance of the training data, which is very promising considering that the equation was not even based off of those data, but of different data, but it still provided very accurate hindcasting, and we should hopefully be able to apply this to forecasting with good accuracy. So overall, almost every model was able to exceed the 90-95% significance level, which is very promising for developing a forecasting model, and that using the 6 teleconnections almost always led to higher skill, most likely due to the 4 teleconnection model only having less capabilities in recent years due to higher annual variability in ice coverage, and that including all variables in a model does not necessarily make a significant impact on the outcomes of the model, as well as the same models can work on multiple reconstructions of the data. And our biggest takeaway is that these models were capable of producing highly accurate hindcasts of ice coverage, and the hope is to extend this into the future and use them for forecasting. Before questions, I'd like to thank CIGLR, GLERL, Mary, Michelle, my 3 mentors for an amazing summer, and I'll never forget it despite having this weird scenario going on, but thank you for everything.
Well, thanks so much, Drew. Fantastic talk, and it's listening to you and the other fellows that presented before you this morning. It's just amazing how much you all are able to accomplish in just 12 short weeks. Coming into this new and ending with something like this is really incredible. So thank you so much. We've got some comments and maybe some questions coming in on the chat. So Philip Chu says, Drew, great work and nice presentation. Thanks for that comment, Philip.
Thank you.
And just waiting to see if some questions come, or feel free to raise your hand as well if you've got, if an audience has a question. Just pausing a moment here to give people time. Okay, I don't see anything coming in. So again, if you've got anything for Drew and I've moved on too quickly, please feel free to enter it into the questions and we'll come back to you later on in this session. So thanks so much, Drew. Great job. And you can go ahead and stop your screen share and webcam.